Good afternoon, good morning, good evening, wherever you might be in the world. This one is actually quite thrilling for me. I've been watching a platform, not really understanding how the company works, but watching a platform quite purely and simply because, as in most things aviation, if it looks right, it probably is right. It's an old saw, but I really think it works. And now Dufour, of which Thomas is the boss, main man, CEO, former search and rescue helicopter pilot, and chief financial officer, I think, for Air Zermatt, is driving and running. And it's I've forgotten the name of it. I should have been more prepared. It's very like that Boeing VTOL with the tilt wing, and that's a bit of an outlier in the drone delivery world. Thomas, how did you? Firstly, thank you very much for talking to me. And then, and Mike doesn't want to talk to me, so but we'll just park Mike for the minute, who you can see on the screen. Thomas, how did you come to going for that tilt wing configuration?
So the original of that comes from our first project, which was the Aero 1 aircraft. That was the first aerobatic electric aircraft in the world that we built in 2015. And we learned an awful lot of things of it. And one of the most important things is efficiency is key, as obviously battery electric flights are limited in energy storage. So that means we came up, we came up with or try to find the most efficient aircraft or transitional aircraft configuration that is possible. And then another element of it is what did fly in manned aviation? What was well flying and proven by pilots who flew it that it is a good aircraft, and that ended up in this tilt wing configuration, which actually comes from the Canadair CL-84.
Canadair,
and the American side as well, the XC-142. So that's the only concept in this area which is proven up to 20 tons of MTOW of these aircrafts. And that is basically what we took as a baseline, and we just electrify it. So we know a concept that is the most efficient one, because it's always creating or producing lift in any state, hover, transition, and cruise, obviously, with the least drag. That is the other important part, especially in cruise. As you know, sticking out lift props in cruise might be good for a very small drone, but the bigger it becomes, the more concerning it becomes. And proven by pilots. So pilots have said, well, it flies actually very well in the transition phase. And that's the reason why we go for this tilt wing technology.
It's as soon as you said it, I thought that is so obvious. It's proven to 20 tons. And I don't mean to dismiss what you said there, but it's just that all the best ideas are generally so obvious once you hear them. But I didn't have that thought. So that was really clever. That is so clever. Of course it is. And so in the transition, for people that aren't aware, so the wings tilt, that goes from here in the hover, and then they tilt forward. So the airframe itself, the airframe is staying in the same position. So the cargo, you're not pitching them forward, not pitching them back.
Exactly.
And so from your helicopter world, what does the transition to forward flight we get, the transition back, is that a bit, it's not, I'm thinking helicopter quick stops, but it's not a helicopter quick stop. Still, this fuselage doesn't pitch much, I shouldn't think. Sorry, I'm not putting that very well.
You can pitch if you want, because to explain quickly, the concept is that's the state of hover, right? So one advantage, you don't have any props who produces download on it, like a tilt rotor aircraft. This download is 30% of thrust that you need to provide additionally from your MTOW to hover. On a tilt wing, you always have a proper airflow, so no download on the wing. And then when you transition slowly, it immediately produces lift upwards, like a wing, right? With the wind, if the air goes flow. So you don't have any turbulent flow around it. That's one thing. But the second one is it immediately produces lift, and therefore you can immediately reduce the power requirements. So not only like the today's most concept, where you have to hover, then transition with more power because you need lift and acceleration, and only then when you're above the stall speed, then you have less energy consume because the wing is lifting your body. In a tilt-wing aircraft, it is actually immediately lifting uplift, and therefore you're always you need massively less energy, which is critical. And on cruise, you don't have any lifting props who are producing drag on the cruise, which is 98% of the flight time. And imagine, I mean, it's the same like flying around with speed brakes. This is terrible in terms of efficiency, and that's an advantage of tilt-wing aircraft. And same goes for back transition, by the way. So as well, you don't have any. You always have a proper flow around the wing. Doesn't matter in which position your wing is. And actually, the angle of attack just basically defines the length of your runway. So there are fantastic VTOL aircrafts, but as well fantastic stall aircraft. So you can land with low stall speeds with very, very few power consumption of it.
And so you'd have a better go-around option then into a cliff top sort of tiny landing on a cliff top, and you're not quite sure because weather or whatever.
Exactly.
So you have a much better go-round potential than
exactly.
Sorry if I have to talk things through to get it in my head properly, because then when that power is coming on, then all the power is coming on for the lift part rather than just a little bit for the horizontal motors. I get it. I'm going to sound like I work for you, but it's such an elegant solution. You can just tell it. You can tell from the look of it that it was right. Even if you don't think of the science of it.
And it flies fantastic. There were more than 100 pilots who flew these concepts, and they were all super impressed about the power, about the control authority, so that they are not only the least energy consumable aircrafts, but as well from the control authority. Give an example: hovering and yawing, so on the spot turning. It's done by the ailerons on the main wing, right? You just deflect the main prop. It's about 3 times more efficient than any helicopter tail rotor. So absolutely fantastic control authority that you have, and you have the whole wing immersed in the prop wash. So you don't have any. So you have as well very good side wind and gust behavior of the aircraft.
So why would they drop them somewhere? I've got the airplane VTOL special here somewhere. They did a special thing on VTOLs, but so why did we favor the Osprey then? Why did they fall out of favor? Because the Osprey's not going to. Because you immediately think, oh well, the Osprey doesn't have this tilting, and then why have Joby and everybody gone for tilting the whole motor and?
So a little bit of history. So you have these two competing concepts: tilt wing and tilt rotor. Tilt rotor, Bell helicopter, Osprey, now V280, maybe the Leonardo 609. That was the American concept. The tilt wing aircraft, mainly pushed from Canada, was the Canadian concept. So main reason why it went to the Army is not invented here syndrome, even though everyone knew exactly that the tilt-wing aircraft is a better performing concept on itself. So this is one of the reasons. And then when they stopped this project, that was exactly as well in the end of the Vietnam War area. So rather than bringing in fast soldiers to the frontier, the concept completely changed towards this clean war, which is obviously an illusion, but it went up to supersonic cruise missile kind of aircraft, and no one wanted to go onto the at the front with soldiers and seeing your own people killing.
So immediately your vision then is, so you said as was it the Canadair one that went up to 20 tons? I don't know which one went up to 20 tons.
The Canadair had about up to 6 tons, and the XC-142 was actually a Hercules, a VTOL Hercules kind of sized aircraft.
So was your head immediately at larger cargo? Was your head jumping past what almost seems traditional 5, 10, 15 kilos now, 20 maybe? Were you looking past that at the bigger thing from the get-go?
Yeah, so we have these 2 different aircraft, Aero 2 and Aero 3. Aero 2, the unmanned cargo or sensor application, up to 40 kilo payload, up to 208 kilo ANTOW, and the Aero 3, which will basically replace helicopter. This aircraft has a bit the size of a today's smaller medium twin engine helicopters. Why? There's a reason for that, obviously. One is, and I'm quite skeptical in this typical urban air mobility market. I honestly don't believe that, because I'm coming from operation, right? Operating helicopter. You know what I mean?
Yeah, it's the weather stuff.
CFO of Aerodynamics for 15 years. And I know what that means. But where it actually makes a lot of sense is when you can replace today's helicopters in specific HEMS helicopters, air ambulance helicopters. Now these helicopters need a certain size and a certain payload, and it's not your urban taxi with 4 passengers. That is not enough payload. So we designed Aero 3 according to these requirements, such that you have a similar aircraft like an Airbus H145 or a Bell 429, which are today the standards for HEMS transport aircraft. And obviously, as the advantages of these aircrafts are that they're much more efficient, much cheaper to operate because they're simple. So these electric propulsion systems, they have some advantages. And then that means you don't just replace HEMS helicopters, but you can tap into the ambulance market, which itself seems to be a small market, but it's actually not. It's a huge market that you can tap in there, but more importantly, in a market where it's needed because you have patients to transport, where it's really critical about timing and so on. And the second one is it's a need, it's an existing market growing with about 10% per year because of the aging, because of the hospital density that diminishes, and so on. And so you have a fantastic aircraft where you have a huge potential at good pricing for a good reason to do so. And that was basically the reason why we designed Aero 3.
And that's, you said it's the size of a twin engine helicopter. Does that include like the wingspan being within the rotor of that? And why I'm saying that, so it will fit existing helipads.
Exactly, as well there. I mean, there are many advantages where we all talk today in this urban air mobility industry about you need to have the infrastructure, heliport. No, you don't need. Every hospital has one. We don't need that. So you just can replace your helicopter with an eVTOL. You need special airways, digital airways. So no, you don't need that. That's common way of flying.
But I think you're in trouble there. You're not towing the party line. You're supposed to be saying that's what you're supposed to be saying as the air ambulance network and all that. Oh, problems, because it blows my mind. You won't know it, but I have a fake vertiport here in my thing, just to try and expose some of the nonsense of what they're saying, of how it would really work with real day-to-day operations of aircraft. But anyway, I'm digressing. I'm very impressed with the concept so far. So certification then. It's probably not too much of a, if I'm taking it words out of your mouth, too much of a certification leap. Okay, it's distributed power. It's a big twisting thing here, but otherwise it's an aeroplane with a twisting wing and distributed power. Is that the sort of it's not, what I'm trying to say is it's not a Joby where it's all modern bonded stuff and tilting stuff without millions of hours of knowledge. Over to you. I'm putting that very wrong.
Yes and no. I would say, in principle, if you have the same needs of certification like a Joby aircraft or like a Beta or all these new kind of electric VTOL aircraft, so you need to certify according to these standards. Tilt wing aircraft have maybe some advantages, and the one is the tilting. That's, by the way, one reason many think, you can't certify that because it has a single point of failure, which is completely untrue. It's actually the only concept that has been certified, and no one knows that.
Yes.
But every airliner is a tilt wing aircraft. Every tail empennage of the tail of an airliner has a tilting wing, and that's the only concept that has been certified in this kind of certification. So airline standards, and so you know how to do it. But then again, you have some advantages, and that's something what people misunderstand. And when you fly helicopter, you know that. Give an example. Every helicopter has a problem with the tail. A fixed tail on where there's a tail rotor of the hitch, because the power need is so big, and you start to twist it so you get cracks and so on. Every helicopter, it takes iteration. Now come with this new nice tiny eVTOL concept where they have all on the edges lifting systems. I mean, this is a structural nightmare for if you have an aircraft that flies 20 years, landing, taking off, and so on. So there is a reason why a helicopter or why an aircraft looks like an aircraft, because the structure has to be important, and has to be sound, and that's in a tilt wing. We have one hinge that we have to certify. A Joby aircraft has 6 hinges that they have to care for, and not in the center, but far off the center on the edges. So it looks simple, but from the structural perspective, a tilt-wing aircraft is much simpler on the structural side. So you have a sound aerodynamic concept, a tilting mechanism that is certified. By the way, the aircraft, opposite to all other eVTOL, can fly manually. So the pilots of the Canadairs flew their aircraft manual. So you don't need a sophisticated flight control system. That is, again, you can.
Yes, so a man in the loop is But so just explain to me. So then you have it's just electric throttles. Just like it was in the Canadair. They were petrol, basically, or just electric throttles.
It is a bit complexer, and you want obviously to have an electric control system. But basically, in the manned version, you just have input-output. So what I put in here.
Is it enough? So a man's able to keep up? In the hover instance with it's electrical controls connected to the stick, but a man's able to keep up.
Exactly.
That's extraordinary.
So that means all the stabilization system that you use on top of it so that it hovers properly is not a flight critical system.
Yes, it's on top of it. I get it.
It's an autopilot, right? Which you have to certify 10 to the -5, not 10 to the -9.
It's 9.
So, and that means the risk is lower in the certification phase, but you have to obviously certify that towards these standards. But there, actually, Aero 2 comes into the game, and what was planned at the beginning, so the small version, what was planned at the beginning as a demonstrator aircraft, at a certain size, not too small, because you want to have an aerodynamic behavior like a manned aircraft, so above Reynolds number 2 million. And that's why the original Aero 2 was just a demonstration and a proof of concept aircraft that we can basically build a modern electric distributed aircraft with electronic flight controls, and that it works in the modern times. But then we had so many customers who said, well, but that's actually fantastic, because this aircraft itself, Aero 2, is a fantastic aircraft. And we started to think, oh, well, actually, it would make sense for two reasons. One, there is a huge market itself. And secondly, as we all know, it costs hundreds of millions to certify this aircraft. So starting with a smaller aircraft, scaling that up, using the technology, using the flight physics systems, which you can prove, okay, Aero 2, that's what we calculated, that's what we built, and that's what we have proven. It's the same. So that means it works as well for the Aero 3 afterwards. And the flight control systems is the same. It actually has the same behavior and so on. So you can build up, based on the knowledge of Aero 2, your production, your certification strategy, your structure of the company, and all of that. And every mistake that you do costs you many hundreds of millions less than it would cost with the manned version that many others do. So we have a much lower budget and can reach our goals with that much faster. We have a product as well quite early, 25, beginning of 25, when the Aero 2 is certified. And as said, it's itself a fantastic aircraft with the 40-kilogram payload. You have two major markets. One is critical cargo, because 80% of the critical cargo is between 10 and 30 kilograms. Yeah. 90% of the US Navy goods to ship, to transport, is below 30 and plus 10 kilograms, as an example. All the critical goods are in this area. So you have a fantastic cargo platform, and on top of it, you have, with a 40-kilogram payload as well, the payload that you can do useful sensor payloads. So give an example, if you have an IR gimbal for detecting forest fires, which is one of the major applications that we see, the small 25-kilogram MTOW aircraft with a payload of 5 kilogram, and you have your IR gimbal with 2 kilogram. Yeah, that's good to watch a fire or see a fire in 2 kilometers distance, which I can do by my eye. But our aircraft can carry helicopter sensors. That's the stuff that you can see a fire in 30 kilometers. So you have a much more powerful detection platform for that. And it will change completely the way how we monitor forests, how we monitor critical infrastructure, how we map, how we search people. So we will have these aircrafts, for example, in search and rescue bases, are able to fly hundreds of kilometers and searching for people at a fraction of the cost of today's helicopters. And that's where we have a huge potential already with Aero 2.
And you're the man that's directly from that market. I must admit, I immediately think of Swoop Aero when I think of you, run by a former Hercules pilot. And now here you are, the helicopter pilot, and been in the thing. It's people, the successful companies in our game are the ones are growing bit by bit, kind of organically, not slowly, but organically and sensibly. Not, wow, here it is, we're going to build this and it's going to be amazing, and we've never flown anything. It's like, no, that won't work. And also, and I'm going to dare to say it, I suspect if you have an issue or a problem, you won't be shy in saying, oh, look, this didn't work. Any company that says to me, no, it flew perfectly first time and everything was great, I was like, really? Really? Did it really happen like that? It's So it's very refreshing to hear your take on things. I know you're a bit pressed for time, so let me just quickly ask you a couple more things while I'm thinking about it. Engine failure after takeoff. What's the single engine failure after takeoff in a multi-configuration? What happens there?
So that's exactly that's actually as well very similar to helicopters. So in the helicopter industry, you have this CAT-A procedure. So you have your takeoff and landing decision point, and before or after you go around, or after in the landing decision point you land. And the same is here. So all these procedures are already very far advanced. So depending on where the engine failure fails, on an Aero 2 actually it's half an engine, not the full engine. So you have basically 8 motors, not engines, 8 motors on 4 props. Yeah. So you lose one motor or one controller or a motor controller or one battery. So you can continue landing. So and you can or when you're in hover, you just go back and land again. But actually, what really is the advantage is it's a normal aircraft. So if you lose 4 motors or 2 props in cruise, you can't afford to lose 2 props in the hover phase. Or well, on the same side, on 2 sides, yes. So you can even lose 2 props, and you still could do a controlled descent and will probably give a hard landing, but you still can do that. On the cruise, you can even fly with 1 prop. It's enough to continue your flight, and then the tilt wing just actually defines the length of your runway, so you can land conventional, like a conventional aircraft on an airfield or in a green field and without any problems. It doesn't mean that you have to pull the parachute or something. It's absolutely a valid way of landing and taking off.
Because I think I was thinking in my head is at what point can you get away with that? At what point is the wing producing enough lift so you can still land forward?
Immediately. So
immediately. Okay.
Every I mean, it really goes down like the power consumption goes like the tilt angle down. So really it goes immediately as soon as you're 10 degrees. So actually the hover position is 85 degrees, not 90. With 90 you go back, obviously. So it always produces in hover, it produces lift 5%, 5 degree angle of lift. And then if it's at 30 degrees, you can already reduce the power by 60%. So it is immediately lifting.
So even in the hover, because you're not all the way up, you have the potential to go forward, but at a bit of a rate. But could you get the nose down and bring it off if you are high enough hover? Or because that beta, the reason I say that, the beta technology, I'm sorry, I jumped in on you, but beta technology say in the event of an engine failure in their vertical stuff, they need 600 feet to transition. That's like a whoa, pardon?
Okay.
Yeah.
Didn't know that. So
that's a bit sporty, isn't it, really?
Yeah. So you really have this, that's the hover part, right? And then you take off, and in that, and this decision point is defined by weight and temperature. So if you're light, you don't even have a decision point. You can, in any condition, you can just transition and go forward. At a certain point, you might not. So you have to go further up. The decision point goes higher up, 100 feet or something. So very, very, very reasonable. And then before, you just go down and land again. And after.
So are you doing the traditional helicopter thing of backing away with the away so you can land back on? Because nobody does that. Nobody does that in the eVTOL world. That blows my mind that you don't see people doing that to land on if needed.
Why do you want that? Because basically you want to have a little slight approach. In the manned version, you want to see the helipad, right? And that's the reason why you go a little bit back. And then you have your power consumption and or power ability, and you just define the rate of descent, probably as low as possible. But if it's a bit higher, you might just But after the decision point, you immediately you tilt the wing, and then you have anytime a go around capability. It doesn't matter what happens. You go around, so it flies anytime. So you don't need, or you just on takeoff, you need this. And that depends on the payload. If the payload is an Aero 2 20 kilo, you don't have any decision point. You can, in any case, transition. If it's 40 kilograms, you need a bit of this.
I'm gonna make this my last question, because I'm feeling I can go on for hours about this. This is so excited. So explain to me, you're lifting the collective there all the time. That's probably your helicopter pilot head doing it. But what will the controls look like in the manned version? Will I have a collective pedals and a stick, or what will I have?
Well, that is a very, very good question. And you have two concepts. You have three. You have the Osprey concept, where you have a plane. So in hover, up means forward, down, backward. Then you have the Osprey concept, or the F-35 concept, where you always pull and then it goes up. It doesn't matter, which is as well. So you need to have a complex flight control system that actually defines or translates that.
Yeah.
And my preferred way is the way as a helicopter pilot flies it. Why? There's two reasons. One, our customers are helicopter operators and helicopter pilots. The second one is, where do you want to have the most intuitive flight controls? That's in hover, close to the ground. And that's where the pitch, pulling up, goes up, pulling down, goes down. If you're in cruise, means then pulling up faster, pulling down slower, like a helicopter. So that is the same. So that's why I prefer helicopter similar kind of controls to fly with.
And how do you handle the transition with that? Is it just automatic, the transition, or how does that happen?
So basically, you define a tilt or a speed envelope that is eligible in with this tilting angle. So basically, you have a speed area like the white flaps area in a plane, but it changes depending on the tilting angle. So if you're hovering, you might be able to fly between 0 and 50 knots. After that, you hit the performance limit, and in cruise it's different. So you have the upper limit is the stall speed, obviously, right? If you are at 0 angle, and everything in between gives you this angle, and you have to keep the speed in this angle. Very intuitive. Actually, is pretty much the same like the V22. And then you will have an additional flight director who is basically keeping your speed in this tilt angle or according to this approach. So then you just say this, you define the speed, and it adjusts the tilting angle of the wing. So this will be the automated version of it.
That's the automated. So then it will keep the wing at the appropriate speed, like the F-111's speed selectors had on their thing. Exactly. So it'll keep it like that.
But it's not critical, because you can fly it manually. You just have to keep your speed manually within that possible range where the aircraft still flies.
Yeah, if it sticks here, more levers just mean you're going to go up like this. Exactly. Less levers meaning you're going to be going,
exactly. And that's this transition corridor, by the way, as well. That's the biggest corridor in where you have in a tilt wing, whereas all the other, this transition corridor is very narrow, right? Coming to lift and push maybe quickly. Again, you have your on the cruise. And then you have to start producing lift gear props just before the stall speed, and the lift props produce some turbulences or whatever. So very aerodynamically, very, very difficult. And on a tilt wing aircraft, you always have this huge transition corridor because it always flies in them. You have always
it's flying in that thing. Well, separate lift thrust is a brute force, really, isn't it? It's relying on the excess power of the electric motors to to compel the thing to fly. It's throwing it off the earth.
Eventually, and that's what you see, and that's what people often misunderstand. They see these small drones flying super agile and very fast. Well, they have all twice or three times the needed power to fly. So actually, a brick flies. But if you translate that to a bigger aircraft, and you can see examples of that, how a multicopter flies when it's big, and then it's not so agile anymore. Then there's a reason why a helicopter looks like a helicopter, actually, right?
Yes, absolutely. Look, I've taken way too much of your time, Thomas. Thank you so much. I'm gonna have to talk to you again. I'm gonna have 1,000 more questions. It's very exciting. And so the reason I like it, just looks nice. And as I say, that generally works in aviation. If it looks right, it generally is.
If it looks good, it flies good. Yes, exactly.
It generally is. So
maybe to finish that up, it looks like a conventional aircraft. And if you see the commercial impact on aviation, have you ever seen an ugly or weirdly looking aircraft being successful? Never. So all the ugly looking aircraft, they might be even very, very efficient or whatever, but they were never a commercial success, because people have kind of a picture of an aircraft, how it should look like. And that's what the people fly. That's where they like to sit in.
You got to cross the border to France, because I think France has been excellent at producing some really fantastically efficient aircraft that look quite ugly, but they've been great. But they've never met commercial success for that exact reason.
or Italy, Giotto P180, for example. Super efficient, great aircraft, successfully never changed. Or a beach starship, duck player, so the Canard, the speed Canard kind of aircraft, looks super good, super efficient, but never was a success. Because it looks weird.
Goodness me! On our weekly show that we do on a Tuesday, we have a rule of red cards. If people are to say things that are too sensible, then they get red carded, and I'm going to have to red card you for that. And you're so right. It's so right. Common sense. That is such good common sense. Because in our world, the reason I said red card, because in the hyped world of drones and electric aviation, it's all nonsense. It's mostly nonsense. So sensible, honest stuff needs a red. We can't have that sort of talk in this world. Not sensible common sense.
and for me, it's important. Tilt-wing aircraft are the most efficient in all areas, and in transition, in hover, in cruise, and that's key. Ultimately, you want to have the most efficient aircraft.
Amazing.
The better the batteries get, the more efficient.
Of course. Thomas, again, thank you very much. We will talk to you again about this, I'm certain. Thank you for your time, dear viewers. See you every Tuesday, 2100 GMT. Bye for now. Bye-bye.
Thank you very much.
Thank you.